So what is the universe actually made of? At the most fundamental level possible. Is it a bunch of tiny separate bits, kind of like pixels on a giant cosmic screen? Or is it one single continuous substance, like a never-ending ocean? Today, we are diving right into one of the biggest showdowns in modern physics to try and find out.
Okay, so let's get into it. For about a century now, physics has had this massive, glaring problem. See, we've got these two theories that are just unbelievably successful. On one hand, you've got general relativity, the undisputed champion of the very, very big. We're talking planets, stars, entire galaxies. And on the other, you have quantum mechanics, the champion of the incredibly small, atoms, particles, and all the forces that govern them. The problem? They are completely incompatible. They just don't play nice together. And finding a single theory that can unite them, well, that's pretty much the holy grail of science.
So, that's how we're going to frame this whole thing, as the ultimate title fight. In one corner, you've got the seasoned veteran, a theory that's been battling it out for decades. And in the other corner, a bold new challenger, coming in with a totally different and, frankly, radical approach.
First up, let's meet our veteran contender, loop quantum gravity, or LQG for short. This theory has been a heavyweight in the world of theoretical physics since all the way back in the 1980s.
So what's the big idea behind LQG? Well, it suggests that space-time itself isn't some smooth, continuous background like we might imagine. No, instead, it's made up of these fundamental, indivisible little chunks. You can think of them as atoms of space. In this view, reality is like this incredibly detailed fabric woven from tiny, tiny loops. And this interconnected web of loops, that's what physicists call a spin network.
So, LQG's game plan, which was developed by brilliant minds like Ashtekar, Rovelli, and Smolin, is to take Einstein's general relativity and just apply quantum rules directly to it. This basically pixelates spacetime at the smallest possible scale imaginable, the Planck scale. Now, a really crucial feature here is that it's background independent. What that means is there's no pre-existing stage for reality to happen on. The network of loops is the stage. This has a huge implication. It totally gets rid of singularities, those points of infinite density, like the one we think was at the start of the Big Bang. Instead, LQG suggests our universe might have bounced from a previous one that collapsed. Pretty wild, right?
And now let's introduce the challenger entering the ring. This one is a newer, pretty provocative idea, and it's called dynamic vacuum field theory, or DVFT.
DVFT comes out swinging with a completely different strategy. It says that everything, space, time, particles, forces, the whole shebang, it all emerges from a single underlying substance. I want you to imagine a vast, continuous cosmic ocean. In this picture, everything we see and experience is just a wave, a ripple, or maybe a whirlpool in this one fundamental medium. So let's look at the tail of the tape for a challenger. It was proposed very recently by Satish B. Thorway, and its core idea is that this one, single, continuous field is the source of everything. Quantum effects aren't fundamental here. Nope, they just emerge from the properties of the field itself. It's a field-first philosophy. The field is the only thing that's truly real, and everything else, including gravity, is just a behavior of that field. And, just like LQG, it also neatly sidesteps the problem of infinities that drives other theories crazy. It just does it in a different way. All right, the fighters are in the ring, they've touched gloves, it is time to see how they stack up head-to-head against some of the biggest unsolved mysteries in all of physics.
Round one, and it's the big one. What is the universe actually made of? This is the most fundamental disagreement between our two contenders, right at the heart of what they are.
And this just lays out the difference perfectly. On the left, you have loop quantum gravity, which says reality is fundamentally discrete. It's built from a network of indivisible units. You can think of it like cosmic Lego blocks. But on the right, you have dynamic vacuum field theory, which says, no, reality is fundamentally continuous. It's a single flowing medium, that cosmic ocean we talked about. We're talking about two completely opposite starting points for what reality is. Okay, round two takes on a true cosmic heavyweight, the black hole. Now, the real puzzle here isn't just what's inside them. It's about how much information they can hold, something physicists call their entropy. Any theory that wants to unite gravity and quantum mechanics absolutely has to get this right.
So, how do they do it? Well, LQG calculates it by literally counting the number of ways its fundamental loops can poke through the black hole's surface, its event horizon. Think of it like counting the threads in a fabric. The more threads that poke through, the more information it holds. DVFT, on the other hand, comes at it from a totally different angle. It measures the amount of twisting in its cosmic ocean as it swirls down into the black hole. Two completely different physical pictures.
But here is the absolute stunner. I mean, this is just incredible. Despite their wildly different approaches, one is counting discrete little punctures, the other is measuring the twists of a continuous field, they both arrive at the exact same number for a black hole the mass of our sun. And it's not just any number, it's the right number. It perfectly matches the famous formula figured out by Jacob Bekenstein and Stephen Hawking decades ago. For both theories to get the same correct answer from completely opposite starting points, that is a jaw-dropping result.
On to round 3, dark energy. This is the big mystery of why the expansion of our universe is actually speeding up. It's explained by something called the cosmological constant, and any serious theory of everything has got to have an explanation for it.
And once again, we see two totally different paths leading to the same destination. For loop quantum gravity, this effect just kind of pops out of the quantum corrections in its cosmological models. And remember, these are the same models that predict that big bounce instead of a big bang. For DVFT, it's even more direct. The acceleration is just a natural consequence of tiny, leftover energy fluctuations in its fundamental vacuum field. And the bottom line is, both of them match our observations. All right, time for a quick bonus round. This one is focused on a question that experimental physicists have been trying to answer for decades. Are protons stable forever, or do they eventually just fall apart? Now, whether or not protons decay is a huge deal. It tells us about the ultimate stability of all matter. So, a theory like string theory predicts they probably do decay, but on an absolutely absurdly long timescale. But look at DVFT's prediction. It's not maybe, it's never. It argues that a proton is like a stable, unbreakable knot in that vacuum field. The physics term for it is topologically protected. So far, our experiments haven't seen a single proton decay, which actually fits both theories, but DVFT makes a much bolder and more definitive claim. So, after 3 intense rounds and a bonus, who's the winner? Let's go to the judges' scorecard and see where things actually stand.
And the result is, well, it's a draw. For now. There's been no knockout punch. As we've seen, both of these theories are incredibly good at explaining some of the deepest puzzles in physics, from black holes to cosmic expansion. But here's the thing. Matching the data we already have isn't enough to win the belt. The real decider is predicting something new, something we can actually go out and test.
So what is the path to victory? Well, this is it. These are the real-world experiments that could finally settle the score. Gravitational wave detectors like LIGO could spot unique signatures in the waves from black hole collisions that are predicted by one theory but not the other. Our telescopes looking at the afterglow of the Big Bang, the cosmic microwave background, could find evidence for LQG's Big Bounce. And the James Webb Space Telescope could find that weird behavior in the universe's first galaxies perfectly matches what DVFT predicts. The answers are out there. We just have to go find them.
Which brings us right back to our final central question. What is our universe at its very core? Is it a discrete quantum tapestry woven from fundamental loops of space and time? Or is it a single, continuous cosmic ocean where everything we know is just a ripple on its surface? Right now, the fight is still on, and the final bell has yet to ring.